which you can search for the command that sets the AS128 key. You can also attack software within the chip, and some of the software is not removable. This is a photograph I took in Texas of the masked ROM of the MSP430 2274. These little dots here are actually vias connecting multiple layers of cross-connect, and every tall column is a bit of significance. There are 16 columns here because there are 16 bits in an MSP430 word, and this is an executable program of about 1 kilobyte, as well as meta information about the chip, such as its model number and revision. This was taken by dropping 5 chips in boiling nitric acid, and then to remove the packaging, and then dropping the same 5 chips without packaging and with the pins having been plucked off by tweezers into hydrofluoric acid, a 5% solution that was also boiling, and removing 1 every minute. The chip, which was timed at 3 or 4 minutes, I forget which, was the one that was perfectly etched. So it removes enough of the glass from above the ROM to allow for a clear photograph without removing the ROM itself. So I built this device, the BSL Cracker, which exploits a timing vulnerability in the bootloader. And because the bootloader is in masked ROM, it's always there to attack. There's a way to disable it, but these 2 chips on the right can fluctuate the power supply to make the chip drop out of the disable while loop. It's like while disabled semicolon, if you were to imagine it in C. And if it ever screws up the jump back to the start of the body of the loop, then it falls into exactly where it would go if it hadn't been disabled. You can extract memory with a debugger. This is the GoodFet 10. I'm now up to the 22 and the 31, and I've got plenty of these boards to give away if you do surface mount soldering. The idea is that you can have a debugger, run a cable over to any sort of board, and then connect to it as a debugger, single step it, dump memory, things like that. This can be disabled. There are ways of getting around the disabling. You can fluctuate the power supply to make it think that its fuse has not been blown. Once it passes that check, it will continue on and let you read memory as if everything were grand. The newer chips, this one here, actually stores the enable or disable word in flash memory. And if it's all zeros or all ones, which are the most likely things to read during a failed fetch, then you have complete access. So if you just enter JTAG debugging with the voltage too low for the chip or too high for the chip, then you're in. And you can use this to repurpose devices. This is a children's toy that I wrote an example firmware image for that a friend of mine, Mike Osman, later turned into a spectrum analyzer for sub-gigahertz. So you can buy this toy for $15, write new software into it, and have your own spectrum analyzer. It's about as powerful as a Y-Spy, but a lot more bubbly. You can do a cold boot attack. So in this device here, which uses the ChipCon 1110, and anything else that uses a ChipCon radio with a microcontroller built into it, RAM is not defended while flash is. So you can connect with the debugger and sort of wipe out the entire chip to write new software into it. When you do this, RAM survives. So you just send the command to erase the chip. This is the exact command line command you would run in Unix. And then you just dump it out to a file, and then you can search that file for the keys or strings or anything else that you think might be within memory. RAM is small. I think we calculated it would take about 4 seconds in Python to try every symmetric key that might be in the RAM. This is a random number generator test for the ChipCon radio. And it's at a period of 7 FFE, so it's skipping a lot of words in between. You'll note that if you go diagonally, 9064, 9064, 9064, 9064, every row is a different sampling, and the random numbers are repeated. And they're repeated every 32,000 and change numbers. This is because there's a 16-bit linear feedback shift register, which is creating all of the random numbers used for key generation. And they're dropping half of it and it gets stuck in one of two redundant cycles because they're dropping either the high part or the low part. So there are only 32,000 or 15 bits worth of starting positions that it might go through in any circuit. This means that the ephemeral key is predictable. In MQV, you generate a unique session key, which you use in addition to your static key for the key exchange. The idea here is that you know the public key because it's given to you as part of the exchange, and you can generate a lookup table, and from the lookup table you can get the ephemeral private key. And by the Leadbitter attack, which I'll get to in a bit, when you have the ephemeral private key, you can then work your way backward to find the static private key. So as this attack will work, the attacker, Mallory, will begin a key negotiation with the victim, Alice. During this key negotiation, Mallory will carefully choose her own public and private key pair to expose individual pieces of the private key. She can make it very small or very large to get a chosen point along the curve. And the victim doesn't realize that this isn't an authorized key until after the exchange has already taken place. And then the shared secret, which Mallory derives, Alice throws out the shared secret and abandons the negotiation attempt. But the shared secret that Mallory derives, combined with the known ephemeral keys of both parties, and Mallory's own known static keys, which can also be chosen in the attack, and the static public key, which is known to Mallory. The only piece missing in that equation is the static private key, and you can work backward to find this. So wherever the ephemeral key is known, the static key can also be extracted in this key exchange. This property is not true of other protocols. In RSA, it's only necessary to ensure that the nonce is never repeatable by an attacker. It's not necessary to keep it private. The algorithm itself used to be part of NSA's Suite B. It was dropped, but there wasn't much of a comment on why. It is sort of a performance hack in that you can use a shorter key. Elliptic curve allows this always. So you wind up passing a 190-bit key around instead of a 1024-bit key, but you get similar levels of security. That's not enough of a performance hack, so ECMQV goes a little bit further. And it does both key validation and shared secret generation in a single pass. So instead of having to first go through and make sure that the public key is signed by the certificate authority, and then go back through and generate a shared secret, you can instead throw it all into one magic little crypto function and be done with it. But this is sold by Certicom, and it might be patented. So none of the ZigBee vendors will actually ship this library directly. They each have their own special email address at certicom.com. So if you want to purchase this library for Ember's product, you email ember at certicom.com. If you want it for ChipCons, you email chipcon at certicom.com. And they're all using the, either the same library or forks of the same library in distribution, which means that if you find a bug in one, you can easily port it to another. If there are timing attacks in this code, and there probably are, it will apply similarly to all of them. So in the case of Alice and Bob doing a key exchange, they each have a static key pair which is shipped with them from the factory. And this is generated on a server in the sky, the same way you'd buy an SSL certificate. You also have to purchase these from Certicom. So these are not generated on the device, and their randomness is not compromised by the problems in the pseudo-random number generator. the ephemeral key pair is compromised.